Good morning, everyone. My name is Arush Gupta. I'm a final year 8 student in the mathematics department, and this is my course project for the course Computing with Signals. So, the title of the project is Image Colorization Using Conditional GANs. So, imagine taking a black and white photo and automatically turning it into a realistic colored image, all with the help of AI. Sounds pretty cool, right? But the workings of how this happens is somewhat a bit complex. Uh, so the motivation for this project started from something pretty different. When the sir was teaching about autoencoders, I found that topic pretty interesting, to be honest. Like how you could compress a data, be it an image, be it something else, down into a smaller representation, and from that smaller representation, turn that and reconstruct it back. It felt almost magical. Like the model was learning the features, or you can say the essence of the image. But after some classes, I started wondering what else we can do with that kind of generative approach. I mean, sure, auto encoders can reconstruct the input image back into itself, like try to reconstruct it back. But can we go further with this? Like, this is one of the very basic app. Can we apply this into doing something else, right? Like, can we generate new data? Can we modify or enhance the image in some creative ways? That's what led me to GANs, or generative adversarial networks. Unlike autoencoders, GANs just aren't trying to reproduce something. They're learning to create something new from the input image. That shift really clicked with me, to be honest. And I started studying about GANs. I watched some YouTube videos, the GANs overall structure and this the how do they work. Mesmerized me, and I decided that for the project I should uh, create a project related to GANs, and image colorization became a really good use case to explore this idea. And this is my attempt to implement Pix-to-Pix paper along with some tweaks and changes for implementing the image colorization. Um, so I have tried to implement Pix-to-Pix paper with some tweaks and changes. For example, I made a new generator model which is different from the original generator model proposed in Pix-to-Pix, and I've made some strategic changes uh, so that which can help reduce the size of the needed data set while getting great results. I've also in the later part I've also used the FastAI imports. FastAI is just a library. Um, so before we jump into the model, there's one important thing: the color space we use. So the color spaces were taught to us like instead of working with RGB, we are gonna use something called the lab color space. So as you can see, this is the RGB color space, and this is the below one is the lab color space. So in lab color space, you've got three channels. The L channel, which stands for lightness, and it's actually pretty close. You can see it's pretty close to a grayscale image. Then there's A channel, which tells you how much green or red each pixel is, and finally there's the B channel, which tells you how blue or yellow the pixel is. So as you can see in the A channel, you must see some tinge of green and at the same time tinge of red. In the blue channel, you must see some blue color and some yellow colors. So yeah. So the cool part is by separating the image, so by separating luminance and color like this, we get some serious advantage, right? The L channel gives us all the brightness information, while A and B channel just focus on the color or chrominance. This means that the model doesn't have to mess with the structure details of the image, which is kind of stored in the L channel. It just learns how to color it. So the job of the model becomes simple. Another nice thing is that the lab uh, color. Space usually gives you smoother, much more natural color transition from RGB. This thing I studied from the paper. Um, th- from the images that I've seen, I felt that this was true. So when the model fills in the color using this, it looks way more realistic. And again, just as I told, from the training perspective, it is also advantageous. Since we have already have the L channel, basically the grayscale image, you can say, we can just feed that as input, right? Then the model only has to predict the A and B values, just like two channels instead of three, like you would need an RGB. So you would kind of get your training data as well. So let's move further. So this is here I've defined the configuration. It's just a dictionary where these are the keys are the parameters, you can say hyperparameters, and the values of them are the values that I've set. I've separated it because you can there's no need to make changes like these changes in the code. You can just go above in the configuration section. You can change the values here only. It kind of becomes easier this way, right? So here we have imported the required libraries. I'm using the PyTorch framework, so I've set the device to CUDA. Uh, Here I installed the FastAI API, and let me shift let me shift here. Uh, yeah, I installed the FastAI API. Here I am loading the data, right? So here I've used the Coco dataset. So in the Coco dataset, it's a very popular dataset, um, and you can easily get this dataset from like just by importing and like yeah. Also, uh, I've not used the whole Coco dataset as it is very large. I've used 10,000 images randomly. And for the first 8,000 image, I've used it as training set, and the last 2,000 as the validation set. Uh, these are the sample images. As you can see, 5 by 5 images. So yeah, now we've got our images. Now we just need a custom dataset class to actually prepare them, right? So I've created this class called image colorization dataset, which inherits from the PyTorch dataset class. This class takes in a list of images, image paths, and optionally a split, train or validation split. Based on that split, we will apply different transformations. Here, as you can see, if the split is trained, we will apply a, a different transformation, and this if the split is val, we'll uh, apply different transformation. Uh, so yeah, here in the get item function, we'll first convert we'll first convert the vector tensor to RGB, apply some transformations in that space, again convert that to numpy array, and then we'll convert the RGB image to lab color space, because remember we would be using L channel as input and the A and B channel as the target. And here's the key part. We'll normalize the L channel to the range of -1 to 1 by dividing it by 50 and then subtracting -1. This is just a standardization technique. This standardization may help the model train more smoothly. And this the length function, just length, returns the length. Pretty simple. Then this is the data loader. Uh, Here we have set the batch size, number of workers, and some other arguments. Here we take the input as take the input will take the input as fogs, and will give it into the image colorization data set, the above class we have defined, and then we'll make the data loader from this with other arguments. So here we are just making train and validation data loaders, and as you can see, the size, if we'll just print out the size of one of them, we'll get, we have 256 cross 256 size image, uh, and we have separated the lumen L part from the AV part. So now let's talk about the heart of the project, a generator. So this is the one of the vanilla generators. This seems kind of seems like autoencoder, but there's few changes in it. Like for example, you have that skip connections here. So here we are using the unit architecture. It's a very popular architecture. Uh, it is generally used for image to image tasks like segmentation, and in our case, we are using it for colorization. So it has encoder and decoder structure. The left side compresses the image down into lower dimension space, and the right side upsamples it back to the original resolution. So what makes unit different is the skip connections. They connect the downsampling layer directly to the corresponding upsampling layer. Uh, this has various advantages. First advantage is that it helps preserve the spatial information. In the upsampling layer, you're kind of giving the spatial information from the downsampling layer to the upsampling layer. So in the layman terms, it might help that upsampling layer somewhat. And this also, and this is, and the another advantage of this is when you are learning, so you must have heard about the vanishing gradient problem, right? If there are many layers and if the learning rate you have set is considered is small, like usually we make use of schedulers and stuff, but if you have set the learning rate constant, it is small, then in the like if as you go back to the layers, the first, second, like the earlier layers, they'll get very small changes in the gradients, right? So the skip connection helps in that. It's just that from that upsample layer, you can directly go to the corresponding downsample layer, and the gradient changes in that will now be considerable as compared to the case when there's no skip connections. So here is that um unit block. So we have got a reusable building block. This is a unit block. This handles one level of encoder decoder pair. We are using convolution 2D layers to go down and convolution transpose 2D layers to go up. So this is the constructor. In the constructor, we are handling different cases, outermost, innermost, and everything in between. The outermost block, as you can see, is the start and end of the full unit. It's where the input first enters and where the final output comes. The innermost block is the bottleneck, the deepest layer in the architecture with no submodules inside. So these are the here's the arguments that if you want to set dropout, what if you want to set innermost, outermost, what are the input channels, what are the submodules, right? Uh, there is um, NF and NI, which is number of input channels here. So yeah, so in this, each block ends up as a sequential list of layers, convolution in which we have convolution operation, normalization of operation activations, and optional dropout, and optional wraps around the submodule, which lets us build the entire unit recursively, right? it's we don't have to define the architecture as a whole if we can use the recursive method. Recursive, like if we define one block and use it recursively. So now we'll move to the unit wrapper class. This is just a forward function, the above one. Now we'll move to the unit wrapper class. This is the class where actually build the full unit using those blocks. Uh, we stack several deepers layers continuously to get the overall unit structure. Uh, right. Uh, so let's move on to the discriminator. This class defines a discriminator network, the below discriminator class. We are using something similar to a patch GAN, which means instead like this is in general, people use vanilla discriminator, but here I have used patch GAN, which means instead of classifying the entire image uh, as real or fake, it looks at small patches of the image and gives a grid of real and fake predictions. This kind of helps focus on the local texture details. So here the model outputs one number for every patch of say 70 by 70 pixels of the input image, and for each of them decides whether it is fake or not separately. And you can see that the using such a model for the task of colorization, this seems reasonable because the local changes that the model needs to make are really important, right? And maybe deciding on the whole image, as in like what the vanilla discriminator do, cannot take care of the subtleties of the task. So this is a discriminator class which defines a discriminator network. uh, it classifies the small patches, if that small patches gives a grid of real and fake prediction. Like it looks at the small patches of the image and gives a grid of real or fake predictions. So the constructor takes in number of input channel, which for colorization will be three, the L channel plus the two color channels stacked together. It also takes a base number of filters, how many down sampling layers that you want, right? Uh, in the then we stack in the model, as you can see, plus is equal to we stack few more layers, each one doubles the number of filters, and we downsample with stride 2, except for the last one, where we use stride 1 to keep things from stringing too much. Finally, the last layer reduces it down to single channel output, the real fake prediction grid. Again, no activation and normalization are applied here. Um so this get layer this is the helper function to define each layer. It adds a convolutional 2D layer, an optional batch norm, and a leaky ReLU activation function. Now let's talk about the utilities function. This is simply the monitoring and visualizing a training process. Because just like if we just run the model blindly, this isn't enough. We need to track whether it's actually learning or not. This is kind of like similar to TensorBoard. If you have, if I'm sure you must have heard of it, TensorBoard, which is used for logging and monitoring as well, right? So as you can see, we have defined the class average meter. This in the constructor resets itself, and in the reset function, you set the counts, average, and sum all to 0. In the update, get you'll get the count. You increase the count by 1. It's like an optional parameter. The sum, you increase the sum to count into value, and the average is like the new sum divided by the new count. So you continuously update these three things until you reset the whole thing by defining the new average meter. So here is the loss. For this is the loss tracking. This function sets up a bunch of meters to track the different losses throughout the training process. As I've told, we are using the helper class average meter, which just keeps a running average of values. So we track things like disk loss gen, which is how well it's doing on fake images. Loss real, how well the discriminator is doing on the real images. Loss GAN, which basically it's the generator adversarial node, how well it is fooling the discriminator. And in it's again disk loss, which is just the all the cumulative loss. Uh, we've got loss GL1, which is the L1 pixel wise loss. So these the loss function here are different. This is the L1 pixel wise loss, how close the generated colors are to the real ones, and then there's loss G, the total loss for the generator, and this is the disk loss is total loss for the discriminator. So we want to return this as a dictionary. Uh, this is the update loss function, where during training we update each of these meters with the latest value from the model, and it automatically averages them over time. This way we can log or plot clean smooth curves instead of raw noisy losses, which won't help our case, right? So since our model works in the lab to RGB function, since our model works in the lab color space, we need to convert the output back to the RGB space to visualize it, obviously. This function handles that only, right? Uh, so this visualize function helps visualize and see difference between the input image, generated image, and the real image. This is just for visualization. And this function is for logging the results. Uh, so here now we move towards our loss function, which is the GAN loss, right? So in the loss function which is used in the vanilla GANs is simply the binary cross entropy with logit loss. This is the PyTorch implementation nn.bc with logit loss. This loss measures the difference between the discriminator's prediction and the corresponding labels. There's also another variation of GAN called LS GAN, where the both generator and discriminator use a least square loss instead of binary classification, kind of making it as a regressive technique, you can say. The loss function used in LS GAN is mean squared error, and this, as the definition of mean squared error is, it measures the square difference between the discriminator prediction and the target label, real or fake label. So this is the generator class that I have implemented. So this takes in various arguments, like what is the GAN mode, what is the real label value, and the ideal fake label value. The fake label value should be zero. I've set it as zero, and the real label value I've set it as one. In the GAN mode, you can have vanilla GAN. You can get LS GAN based on what loss function you want to use. So we'll first register the buffer, and if the GAN mode is vanilla, we set the loss function as nn.bc with logis loss, basically binary cross entropy with logis loss. Else, we set the loss to MSE loss. This is the function to get the label simply. Basically, if the target is real, we'll set the label to 1, and if it is not, we'll set the label to 0 based on the arguments that we gave. Uh, and this is simply the call function where we are returning the loss. Uh, so now comes the weight initialization part. Uh, Before we start training, we need to initialize the weights of a model. This turns out to be an important step because how we initialize the weights can really affect how well and how quickly the model learns, right? So this is the init function. This is responsible for initializing the weights of the neural network. Uh, we have set three different types of initialization: norm initialization, Xavier initialization, and Kynman initialization. Uh, yeah, so these three are various very popular weight initialization techniques. Uh, we have also set if we have also set the batch norm 2D. If it is in the class name, we'll set it. Otherwise, we won't use it. But I have used it here in the training in my training. So putting everything together, the this is the main model class that I've defined, where I've put everything together. Like this is whole of from the config that I defined earlier. This is whole of the parameters. This I've defined discriminator. This is GAN. I've just defined discriminator, L1 laws, GAN laws, optimizers. Here I've used Atom optimizers, which is also one of the very popular optimizers. I've defined some helper functions like requires gradient, self set input, forward function, backward function, and backward function for a generator, backward function for discriminator, optimize function. Yeah. So this is like I've put everything, the little things that I've defined into one main model class. So another thing is the train model. Here I basically train the model. I use the data. I take epochs as input, train loader, and the model. So this is basically the training step. So here in this, I just use above and train the model. So as you can see, you can check each of the losses that I defined above, and this is the image. This is the white and black image. This is the reconstructed colored image from the model. This is the original image. So as you can see, this is just the first epoch, and the model is kind of, you can see, start coloring. The results are not good, obviously, because it's the first epoch, but the model is starting to color the image. Again, I haven't implemented it for much epochs because the training in GAN is a very slow process. So I it was taking too much time, so I didn't implement. I just checked the results, final results. As you can see, as the epochs getting bigger, like more more for the more training, the output is, gradually improving the coloring of the image. Um, so yeah, these are the results that I'm getting. Obviously, if we train the GAN for larger number of epochs, we'll definitely get better and better results. This is just because the generation part is a bit tough, because it's in generally the GANs, the generation part, the work of the generator is regarded tougher than the discriminator part. So the discriminator sometimes outweighs the generator part, right? So this is the one of the disadvantages of using plain vanilla GANs. Uh, so these are the results, and this is another approach that we can use instead of training generator from scratch. We can use FastAI imports and Torch Fusion module to build the generator model. We can use here, like for example, I have used a ResNet, which is again a very popular model in the in the CV space. I've used ResNet, which is pre-trained on the ImageNet, and I've added this as a backbone of the unit generator. The discriminator that I'm using is same as before. So this is the short code for that. In this, I just replaced I kept everything the same. It's just I've changed the generator architecture. Yeah. So this was it. This was my project, and yeah, I learned a lot from this course, to be honest. And from this course, learned about I got interested in automobiles and learned about GANs. So this was one of my like attempts to, you know what I've learned, transferred into the code. So yeah, thanks. Thank you.